Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. We've got a lot of videos out there on the Coriolis effect in the debunker community, and everybody seems to be pretty comfortable with north and south deflections due to Coriolis. Everybody's got a pretty good grasp of that. But a lot of people are asking me questions about east and west. So I thought I'd go over that today. Another thing people are asking me is, Bob, why is it that you have an image of the moon in the background of a video on Coriolis? Well, it's because Apollo 11 gives us the answer when it comes to east and west Coriolis. So let's cue up the music and get going. Well, when trying to deal with a new concept, one of the best ways to start is start from something that you're familiar with. Now, many of us understand Coriolis when we're moving from south to north or north to south, and let me give you an example of that. Say you're in an aircraft and you're taking off from the equator and heading north to the 45th parallel. Now, when you leave the equator, your aircraft is moving from west to east at 1,038 miles per hour. By the time you get up to the 45th parallel, say Gaylord, Michigan, the rotation of the Earth at that point is only 734 miles an hour. However, you're still retaining this west to east velocity from when you took off at the equator. And as a result, what will happen is your path will curve to the right. Now, in the northern hemisphere, Coriolis causes objects to make a right curve, and that is whether they're going north or south. Now, this curve is caused not by any actual force, because Coriolis is what they call an apparent force. But what's happening is you have a certain lateral speed on the equator, and as you go north, the ground slows down underneath you, and as a result, you curve to the right. Now, likewise, if you're going from the north to the south, you start off at a slower rotational speed, and the Earth starts rotating faster underneath you as you go south. But here's where it gets interesting. What if you start off at one location on the 45th parallel and go down to another location on the 45th parallel? Why is it that as you fly from west to east, you curve to the right, or if you fly from east to west, you also curve to the right? How does Coriolis work when you're not moving from north to south? The rotational speed at each of these locations is exactly the same. So why is the curve occurring? To answer that question, we need to go to the moon. Okay, so here we are in lunar orbit, and the Eagle is firing its rocket engines in the opposite direction of its path of flight. What happens? It begins to descend. Now, why is that, and how does that affect Coriolis? Let's have a look. Well, let's start off with a little bit of theory. Now, when your force of centrifugal force equals the force of gravity, you're in orbit. That's just as simple as that. Now, the reason that is if you look at the surface of the Earth or an orbit or anything, you have the force of gravity going down. And as the surface rotates, you have centrifugal force going in the opposite direction. When these two match, the force is zero. And basically, you're weightless. That's the definition of what an orbit is. Now, what did this mean for the Eagle, and what does this mean for Coriolis? Let's have a look. Now, an easy way to look at this is look at what centrifugal force is. Centrifugal force is equal to the mass of the object times the velocity of the object over the radius. And for an object to be in orbit, that has to equal the force of gravity. Now, as you recall, the mass of the object is also in the formula for the mass of gravity, and they cancel each other out. So when you look at orbits, the mass of the satellite doesn't really come into play. So let's go ahead and rewrite this a little bit. Let's get rid of that. And let's add a little thing there to say that those two are proportional to each other. So what does this tell us? The force of gravity acting on an object in orbit is pretty much a constant unless you really change the orbit significantly. Now, we'll go into that when we go into Kepler's laws and the orbit of satellites. But for now, let's just say the force of gravity is pretty much a constant. What happens if you increase the velocity of the satellite? In order for that to remain equal to the force of gravity, you have to increase the radius. Likewise, if you decrease the velocity of the satellite, in order for this to remain in balance, you have to decrease the radius. And that's the radius of the satellite to the center of the Earth. It's not the height of the satellite. Now, this is not exactly accurate, but it's close enough to demonstrate this principle. All right, now what does this actually mean? Say that you have a satellite in orbit around the Earth, and here it is. It's that certain distance above the surface and a certain radius from the center of the Earth. And it's going along at a steady speed. It will stay that distance above the Earth as it goes all the way around the Earth and maintains a circular orbit. But what happens if you speed the satellite up? Well, if you increase the speed, you have to increase the radius. So what will happen is as you speed it up, the satellite will go up into this higher orbit. Likewise, if you slow the satellite down, again, decrease the speed, decrease the radius. So what you're going to end up doing is bringing it down to an orbit like that. Now, another way of looking at that is you look at the angle formed by the starting point of the spacecraft and the ending point. No matter what you do to change the speed, you have to conserve the angular speed. And if there are no other concerns, it'll do that by changing the orbit. So say you speed up a little bit here. So instead of going from here to here, you end up going to there. The problem is that would increase your angular speed, all right? You don't want to do that. What you want to do is you want to move upward until this angular speed is that long. Okay? Likewise, if you slow down, you chop off part of this, you have to bring it down to a point it'll still fit in the wedge. Okay, so here's the situation in July of 1969 before the moon landings. You've got the command module and the lunar module up here in lunar orbit. Now, they're buzzing along at about 6,000 miles an hour, and they're in an elliptical orbit around the moon down here. Now, the idea was to keep the command module in orbit around the moon, so it's going to stay going along at about 6,000 miles an hour. The lunar module separated from it, and it had to slow down in order to land on the moon. So what it did was it fired its rockets in the opposite direction of travel. That's the way they're all traveling. And it fired its rockets in the opposite direction. As a result, it slowed down. Now, when you decrease velocity, you decrease radius. So what it did was it started descending. As it slowed down, it got closer and closer to the moon, to the point that it matched the rotational speed of the moon and was able to touch down. When Neil Armstrong and Buzz Aldrin were done taking pictures of everything except the stars and picking up dust, as Jaron would say, what they did was they blasted off the moon. They left the descent module on the moon and took off in the ascent module. That had a little rocket motor on it. So it went up, and then it kind of went off to the side and started going in this general direction. But it did it under rocket power. It was constantly accelerating. So as it increased its velocity, it increased the radius from the center of the moon. And as a result, what it did was it started climbing, and eventually it caught up with a command module in orbit. They docked, transferred people, and off they went. Now, what's this have to do with Coriolis? Let me show you. But before we go on to Coriolis, let me just put in a quick word about good old Buzz Aldrin. Everybody talks about Neil Armstrong because he was the first man on the moon. Everybody talks about Michael Collins because he was left up in the command module and didn't get to set foot on the moon. A lot of people don't talk about the second guy to step foot on the moon, and that was Buzz Aldrin. Now, Buzz is an interesting guy. He was a fighter pilot in the Korean War, shot down a couple of MiGs, in fact, and actually made a story in Life magazine for doing it. Now, when Buzz came to NASA, they were training astronauts for spacewalks using a series of bungee cords. Buzz Aldrin was one of the people that helped pioneer what they call the neutral buoyancy pool, where they trained them in water in a near weightless environment. Now, perhaps one of his most important contributions to NASA was his work for his PhD thesis from MIT in 1963. He developed many techniques for doing orbital rendezvous using the same equations that we just used. Now, obviously, his approach was much more thorough, which is why I used a whiteboard, and his doctoral thesis was 311 pages. But the point remains that they are essentially the same, and we can thank Buzz Aldrin and Sir Isaac Newton for that. Okay, back to Coriolis. Now the fun begins. Say we have an aircraft going from west to east above the surface of the Earth. Now, it's going along at a higher velocity than the rotational speed of the Earth, which is in that direction. So the plane's velocity is the rotational speed plus the airspeed. That's faster than the rotational speed alone. As a result, what's going to happen? Well, we've increased velocity, so we have to increase radius. Now, that would cause the aircraft to want to tend to go upward. However, the problem is the aircraft has to operate within the constraints of the atmosphere. So here we have the Earth. Here's the aircraft. It's moving this way, and it will curve downward towards the equator because that is where the radius of the Earth increases. It's maximum at the equator, and it's higher than it is at 45 degrees north. So if you can't increase your radius by going up, you go to a place on the Earth that has a larger radius. As a result, it will curve to the right, and that's the Coriolis effect. Likewise, if the aircraft is going from east to west, it's slowing its velocity down, and as a result, it tries to decrease its radius. It can't fly downward into the ground, so it goes to a place on the Earth that has a smaller radius. Specifically, it starts heading towards the poles. So I hope that was able to answer a few lingering questions you may have about Coriolis. I have to be honest with you. I was a little confused about the east and west turn for Coriolis myself until I read a couple of papers on this. Now it all makes sense to me. Now, just for good measure, let's mention something called the Iotvos Effect. Now, as you recall, centrifugal force is the mass times the velocity squared over the radius for objects going around a circle. Now, we have a rotational speed of the Earth. If we are in an aircraft going from west to east, our centrifugal force will increase. And as a result, more centrifugal force will occur in the opposite direction of gravity. The end result is that if you fly from west to east, objects weigh less on the aircraft than they do on the ground. Likewise, if you fly from east to west, you are decreasing the velocity in respect to the rotational speed of the Earth. Centrifugal force decreases and does not take quite as much away from the force of gravity going in the opposite direction, and objects will weigh more. There's some very good demonstrations on Wolfie's channel for this, and I've actually done this myself and verified it. That does make a difference, and it is measurable on an aircraft with a scale. Now, the reason I say it makes a difference with a spring scale is that it works by compressing a spring. On a balance scale, such as this, it won't make any difference at all because both the reference weight and the mass you're weighing are affected exactly the same. So you won't see a difference. That's why spring scales need to be calibrated based on latitude, but beam balances do not. That's why they measure precious metals using beam balances, not spring scales. So this is Bob the Science Guy signing out from Northern Michigan. Thank you very much for stopping by. Remember, hashtag best use of whiteboard. Remember to hit like and subscribe to my new channel, and I'll see you again soon.
Mama, please make them hear me, or I can't teach them anymore. This rabbit hole's too deep for